Hello everyone and welcome to NSTA Web Seminars where you can find live interactive learning at your desktop. This program is titled Preparing for the Next Generation Science Standards, Developing and Using Models. And our presenters are Christina Schwarz and Cindy Passmore. My name is Bryn Slate and I will be moderating today's program. Due to technical difficulties experienced during the original presentation on September 25th, this is a re-recording of the program. I'd like to remind everyone to visit the NSTA Learning Center, your online portal for over 9,800 resources for science educators. You can access over 3,200 of those for free in the Learning Center, and you can add them to your library to access later at any time when it's convenient for you. Our community forums are also available to continue the discussion there with your colleagues, and our online advisors are there ready to assist you. We also have tools to plan and document your professional learning and help you reach your goals. And it's all available there at the Learning Center by going to learningcenter.nsta.org. And now I'd like to introduce today's presenters. Ted Willard is directing the National Science Teachers' efforts around the Next Generation Science Standards. And Christina Schwarz is with us from Michigan State University, and Cindy Passmore is joining us from the University of California, Davis. And now I'll turn it over to Ted.
Thank you, Bryn. I want to just start with my little homage to Star Trek: The Next Generation, which I always think of when I hear Next Generation Science Standards, but to move and give just a quick overview of the development of the standards and sort of set the stage for Cindy and Christina. The standards themselves are an effort of 4 organizations: the National Academies of Science, the National Science Teachers Association, the American Association for the Advancement of Science, and Achieve. These standards, there's sort of 3 phases for all of this. We have the academies actually developing the framework for K-12 science education, which came out in July 2011. There's the standards themselves, which Achieve in a consortium of 26 states are working on. The first draft of that came out last May. Another one will be coming out about a month from now. And then that will be feeding into and providing what is necessary to create assessments, curricula, instruction, and teacher professional development and pre-service education for teachers. Here's a little closer look at that set of states. You can see which ones are involved. When the standards are completed, these states have promised to seriously consider making use of them. They are the main people involved in making decisions around the development of the standards. But the states not in blue, the gray, still also have an option to adopt these standards once they are completed. As I mentioned, first draft of the standards was in May. Second draft will be coming, looks like mid-November to late November. The key point here, it's not out yet. We're still waiting for, we cannot be talking about the final different standards, which is why a lot of our work here will be referencing the framework for K-12 science education. This was done by a committee of scientists, including some actual Nobel laureates and science educators. It is available free, a PDF of it from the National Academy Press. You could also get a copy from NSTA Press in the NSTA store. 3 dimensions are discussed in the framework. There's scientific and engineering principles, cross-cutting concepts, and disciplinary core ideas. The practices themselves are ideas in terms of activities that science engage in to understand the world and things we want our students to be engaging in. This whole series is focusing on these practices, and this session is specifically on the practice of developing and using models. Cross-cutting concepts are aspects that cut across all different areas in science. You can see on the list here. And then the disciplinary core ideas, pieces that we are probably more familiar with is standards. What people most think of as the content. Life science, physical science, earth and space science, and then something a little bit new, engineering and technology. Here is a sample of the standards from the May draft, where you have a performance expectation described here. And this performance expectation takes advantage of the three elements below it, those three dimensions in the framework, so that there are some aspects that deal with developing and using models, constructing these models to explain that. The content then comes in, that atoms combine to form new substances of varying complexity. And then we move on to this idea of a common theme, in this case patterns, that we have repeating units in terms of how atoms and molecules combine together. All right, so with that basics, I'm going to turn things over to Christina and Cindy, and I hope you enjoy what they have to say.
So thanks, Ted and Bryn. My name is Christina Schwarz, and together with my colleague, Cindy Passmore, we're going to be presenting information today about developing and using models from the Science Education Framework. And much of our work derives from some of the funding that we have from National Science Foundation and other places. So first of all, a little bit of background about who we are. I'm a professor in science education and teacher education at Michigan State. I have a background in science, and I did my graduate work with teachers and students around scientific modeling with 7th graders in physics using microworlds. I've done most of my work in the past 15 years around scientific modeling and supporting teachers and students at primarily at the elementary and middle school levels. And research and the demonstrations of scientific modeling that I'll be talking about today come from some of my most recent work around this.
And hello, my name is Cindy Passmore, and Associate Professor of Science Education at the University of California at Davis. I've been here this is my 11th year, and prior to that, in my earlier career, I was myself a high school science and math teacher, and then went back and began working on this problem of how to make classrooms more authentic to what actual scientific reasoning looks like. And have been working on that in the past 15 years, most recently working with in-service teacher professional development. I also do pre-service teacher education and student learning research. But my most recent work has been with a cohort of about 60 teachers trying to figure out how we enact modeling in classrooms. And so I'll be drawing on that work today.
Okay, so we want to start off by telling you why we love scientific modeling so much and why we think you should as well. We're passionate about modeling for a number of reasons. So first of all, modeling is at the core of science and much of engineering as well, and it uses a lot of mathematics, so it converges quite a few of what people are involved with in STEM. And one of the wonderful things about models and modeling is that it really enables us to link theories with data. So there are ways of mediating data and as well as the theories behind them or ideas. And also they make our thinking about these two things visible and workable. And obviously, we think that modeling can help learners also advance their ideas and understand science, and it can help us teach science better as well. And so some of the teachers that we work with have said things like, this is the way students should learn, this is what we think, science is all about. Cindy has a biology teacher she works with that said models are an amazing way to focus students, to make them think about how things in the world work and why they work that way. Models make students put small concepts together in the larger picture. They help students tie the knots between pieces of string to make the larger rope, so the connections between the smaller and the bigger can be seen. So we think that idea of sort of providing coherence and making thinking visible and workable is very important. All right, Cindy.
Okay, so we wanted to begin by just sort of situating ourselves and where we're coming from, and in particular because the first of these webinar series was hosted or presented by Brian Reiser, who was on the framework committee, and so he was able to answer questions about how and why certain decisions were made in the framework. And so we just wanted to begin by saying that Christina and I were not on that committee, and we come at it from, as all of you do, as users of the framework, and what we're trying to do is take our expertise that we have developed over a number of years working in this area of modeling and interpret the framework in light of that background. And so we just wanted to bring that to the fore and also mention that most of our work has been done in scientific modeling, and while we have some ideas and thoughts about engineering modeling, it's going to be less of a focus here.
Okay, so we have a poll to begin our conversation, which is, what is the most common way that you use models and modeling in your classroom? And Bryn, should we continue with this poll right now?
Sure, Christina. Let's go ahead and get some feedback from folks and see what they say. So everybody, your poll buttons are now active at the top of your participant window. And if this question suits your situation, if it's applicable to you, go ahead and give us an answer, and we'll see what we can get.
And if you're not currently in the classroom, just go back when you last were in the classroom.
That's great, Ted. So the folks who are no longer classroom teachers, maybe think back to when you were teaching there. And I'll go ahead and give just another moment before locking those and putting those responses up so Christina can have a look there. And we can all see what we have. Okay, and Christina, back to you.
Okay, so it looks like we have quite a range of folks who've done different things with models, which is terrific. I think commonly many teachers use models and modeling to show what some aspect of a phenomena looks like and to help students remember or reinforce ideas presented in class, maybe not reflected in this poll right now, but less common is to assess students' ideas, although we find that models and modeling can be very useful for that. And we're going to emphasize D, which is to help students develop or reason with ideas through modeling. And those, in turn, I think, help with all the other aspects. So that's primarily how we're going to approach it today. Okay, so let us give you an overview of our session today and what we hope to accomplish. So first we want to share a little bit about how we define what a model is and what the practice of modeling involves. And then we're going to talk about why we think, again, modeling is really important for students to be engaging in and for us as teachers to be teaching with. And Cindy's going to tell us a little bit more about how modeling fits in with the rest of the framework, which is really important for us to make sense of all these practices. And then we're going to illustrate several examples of modeling in the classroom with an elementary or an upper elementary and a secondary example of modeling to highlight some of the features. We're going to share some resources with you, and then we'll have some discussion at the end to address any of your questions that might be remaining. So let's start off with what exactly is a scientific model. There's the word itself is somewhat confusing, and there are many different ways of defining it. But we think of a scientific model as an abstract, simplified, often representation of a system. So a system is really important. It's got lots of components and relationships between those components. But what a model does is it helps to make features of that system and relationships explicit and visible. Often models have aspects that are invisible. Sometimes things are too fast or too slow or too small or too large. These tools will help us think through and test ideas about those systems. And they're very importantly used to make predictions and explanations for the world. If they're just illustrations, they often can't help us quite as much as if they have more to them and can help us make predictions and explanations. Generally, people think of two types of models. The frameworks talk about internal or mental models, which are the internal models in your head that you can think of as working to think about how the world works. And there's also the second part, the conceptual model, which is what the framework calls it, or what's expressed out in the world. And those are things like diagrammatic figures, tools, or tables, things like that. In fact, the next slide, I'll give you some more examples of what some of those might be. We have the Bohr model of the atom, which is a fairly common way of thinking about a model, or the particle nature of matter. And in elementary school, you might see more commonly light ray models, water cycle models, food web models, and interactions between organisms. There's also, I'm going to move it back because there's a couple of other types of models. Computational models of the atmosphere, often used nowadays for climate change, in biology, natural selection models, and ecosystems, protein synthesis models, things like that. And engineering uses models for analyzing and testing and designing. And I do want to mention that charts and graphs and other kinds of data modeling are also possible. We tend not to emphasize those in our presentation today because that's not what we've worked with more directly, but those are great examples of types of models. And what we want to emphasize is even though we work with the expressed or conceptual models that students interact with in the classroom and that we help them think about in the classroom, what we really care about is advancing their own mental or internal models of how the world works. So it's important to realize that it's not actually the product, it's the process with the students that matters. So how can we help them productively engage in this practice? Because at heart, modeling is about using tools to make sense of the world, and we don't want to forget that as we're thinking about how to do this practice. What is modeling as a practice itself? It's basically the practice of testing and revising models. But what does that mean? Well, an easy way to think about it is that it often involves developing or constructing a model that embodies aspects of theory or evidence, evaluating that model against empirical evidence or theory, known ideas, using the model to illustrate and predict or explain, and then also revising that model. And again, it's fairly common in the classroom to engage in the using models. So for example, if I have a model of the eye or the cell, to help my students understand what that looks like. So using is a fairly common thing. Also developing models or constructing models. So for example, if I want my students to really understand the planets in the solar system or the components of an ecosystem, I might have them develop a model. Somewhat less common is actually evaluating and revising models, which we think is really critical to getting students' ideas to change and to helping them understand what the practice is. But along with those practice elements, we also know that it's very important for students to understand what it is that they're doing. So for example, what's the purpose of the model and modeling that I'm doing? It's to explain this question that we have about the world. And furthermore, we think it's really important for the social aspects around modeling to be highlighted and to be made visible and to be worked on explicitly. So for example, as a group, let's talk together about how we're going to evaluate and revise these models. What do we want? What do we think is important about these models? Let's make them consistent with evidence. Let's focus on the mechanism. That'll help us tell us why things happen. So those are important aspects of the practice itself too. And to briefly, again, revisit why this is important, in the framework it actually says, and we agree, that this and other practices help learners establish, extend, and refine their knowledge. So that's consistent with the idea that engaging in this practice will help them understand more about the world and refine their knowledge of the world. It clearly, enabling students to embody their ideas and evidence into representations helps them extend and revise their ideas. So in that sense, it helps them advance their subject matter knowledge. Because it makes mechanisms and components visible and testable. It helps them better understand the way science works. Often it's not clear if you look at a textbook why something is known or how it's known. So by engaging in the practice of testing and revising these ideas, then they can better understand how science and engineering works. And then, again, as we said before, it can help them develop these sort of practices and skills involved in thinking about systems as a whole, and what's involved with them, how they interact, how to share and evaluate one another's ideas. It's not just based on the fact that everybody likes Frank in the corner or somebody else is yelling really loudly. We have to think about evidence and mechanism as we're evaluating these models. But we understand that the actual practice of models and modeling can be difficult for students and teachers to understand and even enact. So we're going to try and help share some ideas about that today.
Okay, and so when we look at the framework that Ted mentioned at the beginning and that is forming the basis of the construction of the next generation science standards, we see that the authors of the framework have identified 8 core practices in science and engineering, and these are listed here. And what we want to do today is talk a little bit about the connections we see between and among these, in particular with regard to modeling. And so for lots of reasons, the developers of the framework have listed these. And what we want to say is that we see these not so much as a list, but as a dynamic, interconnected set. And if we look at really how we see science, the outcome of science is the development of models and theories in order to explain the world. We're trying to make sense of the world, and we do that by developing models and theories. And so how does that relate to the other practices? Well, we would say that to begin with, we have in our minds some ideas about how the world works. We don't start as blank slates. We don't start with looking at the world completely without any prior ideas. And those models are often implicit, but they guide us in what kinds of questions and problems we notice and define in the world. And so just what it is we're noticing and the kinds of questions we ask, that process is mediated by models. Models then also help us decide from those questions what kinds of empirical evidence and investigations we might carry out to help us refine and come to further develop our ideas about how the world works. And so those models we have are also the filter through which we analyze and interpret the data that we get when we engage in investigations. And of course, those data then feed back into our models, help us refine our models, and it's from there that we're able to develop explanations. And this is probably, the key outcome that we want. This is the sense-making part that's so important in science, when we can come to some idea about how the world works or how the aspect of the phenomenon that we're exploring actually works. And then there are a number of ways we can think about this. This particular framework comes from Andy Anderson and his colleagues at Michigan State, and it's just a way of thinking about where models come from and how we then use those. And so you notice at the bottom of this pyramid here, we have all of our experiences in the world, millions of experiences that we have every day, and the observations we make of the material world, of the world in which we live. And it's from those experiences, those observations, that we then distill that myriad set of things down into a set of patterns. And those patterns become really the focus of what we're trying to explain. They are the phenomenon we're trying to understand. And from there, we can develop some key models. And so that is, as you see on the left side of this pyramid, or triangle, I guess it is, we see this focus upward in the inquiry process, from observations to patterns to models. And then once we have models, we can then turn around and apply those back to the patterns and observations we make of the world. And so that's the sort of right side of the triangle there when we think about the application side. And it's this sort of iteration between the development and the application of models. It's really the central hallmark of scientific reasoning and how we think with models in the sciences. So a few other connections we'd like to make sure we're establishing here is that we both use mathematical representations to illustrate and distill some of our ideas in models, and we also use computational reasoning to think through the relationships between aspects of our models. A key part of developing and using models is the social aspect, as Christina mentioned, and when we are trying to come to some consensus, understand and develop our ideas more fully, we engage in argument. And those arguments in science are always with regard to the evidence that we've gathered and the information that we are bringing to bear on our thinking and the models we're creating. And of course, ultimately, we want to be able to communicate and evaluate the information And so a key part of developing and using models is this communication aspect. But we want to emphasize again that often it's merely this one that is the focus of a lot of the modeling that's done in many classrooms in which we work. And so that is more on the using end than the developing end of models, just showing people models that are completed. And that's not really the hallmark of what we're talking about here is the reasoning through the ideas and putting them together and understanding the relationships, communicating those, thinking about them with regard to the data and evidence, and then finally communicating them. Well, I mean, obviously communicating all along the way, but that communication outcome is not the only way in which we use models. And so if we think about this messy diagram, it's just meant to show that really the way we see it is that the models are really one of the central organizing practices of this set of 8, and you can imagine some people have different sets or ways of talking about scientific practice, but that models are really at the center of the scientific endeavor in the sense-making that we're trying to do about the world. So again, just to come back to the framework, we're reminded that they serve the purpose of being the tool for thinking with, that models are really reasoning tools, and they allow us to understand and distill into a usable format our current ideas and thinking about how a particular aspect of the world works. So we think some of the key elements of modeling in the classroom are really around these kinds of cycles that we might conceive of. So if we think about developing ideas, evaluating those ideas, and revising those in a social setting, that's one of how you would know if modeling was going on in the classroom. You would see those kinds of cycles going on, and students grappling with and struggling with their understanding of how some aspect of the world works, making their thinking visible, collecting evidence, and squaring that evidence up with their theoretical understanding in developing and furthering their ideas. And then thinking about models as existing as not these sort of a single model existing by itself, but that models exist as part of a suite of knowledge we have about the world, and that that each model, as we begin to think through it, needs to be consistent with and evaluated against other ideas we have about the world, and of course, always against the empirical information that we are gathering. So we want to spend a little bit of time. This word, as Christina mentioned a few moments ago, model, is used in a myriad of ways in the English language, and none of those are wrong. But we do want to focus in on modeling as this sort of reasoning and active cognitive endeavor, and not so much on the physical materiality of the models themselves that sometimes we talk about in science classes. And so we want to kind of make this distinction between models as reasoning tools and models as kind of art projects or things like that, of that nature. And so sometimes we can think about constructing these physical replicas of the world, and that's a powerful and has its place certainly in science classrooms. But that's not the kind of modeling that we're talking about right now. What we want to think about are sets of ideas that are useful in predicting and explaining how a system works. And therefore, those ideas become dynamic and interactive with one another. And you can see, in your sort of typical cell model, styrofoam cell model that might be made in the classroom, or Jell-O mold model or whatever, that the interrelationships between and among the parts of the cell are not evident either in that replica or most often even in the instruction that's surrounding that. So what we are looking for are models that help us answer questions about how or why a system works the way it does, and not merely describing the system. And so to reiterate, these kinds of diagrams and equations and three-dimensional replicas are things that are quite useful in envisioning and clarifying some ideas, but they only become models in our view, in the way we're using that word, when they are actually used to reason about the underlying system and not merely describe it. So that's kind of an important distinction in the work that we do, and one that we think is really going to be key as we take this modeling practice forward as a frame for science education. So again, to come back to the framework, there are a number of goals, but that really this notion of explanation and prediction is an essential part of how we want the modeling to be picked up and thought about, and that learners by the end of their schooling should be able to use models to explain and predict. So we have a moment to pause here for some questions, and I see some that have been popping up on the chat as we've been going, so I think Ted will moderate some questions for us.
Great, thank you both. I'm actually take a little bit of a point of privilege here because I realize I'm having some important realizations here. I want to check my understanding, see if everyone else's understanding is the same here. When we look at slide 49 and we have a student diagram as is drawn here, it's not so much that this diagram is the model that we're talking about, but really it is a representation of the student's model, or if I really want to tie up the words, a model of the model. Is that a correct interpretation? Let's ask Cynthia for that, since it's her slide.
Yeah, I think that is the way we've worked with it with teachers. And to just clarify, again, it's not that it's incorrect to call this diagram a model. And in fact, in most classrooms, that is how it would be described. What is your model? And you draw it there. But what we have found very useful in working with students and teachers is to emphasize that what this thing is doing is it's representing our ideas about how this works. And so the judging that we do about this diagram shouldn't be about how neat or sloppy the writing is, or about maybe the way an arrow is drawn may be very important, or it may just be an artifact of poor artistic talent on the drawing. And so that we want to make sure that we're critiquing the ideas and the understanding and the relationships that are being illustrated by this kind of a diagram. And so I think that distinction that you're making is, I find it to be an important one in our work.
Right, and that I just wanted to add that that's the distinction between the internal or mental model and the expressed or conceptual model that the framework talks about.
Great, and then to continue that point forward, the problem with an art project like that is shown here in terms of all of this is sort of the same problem that would exist if I had a very good scientific explanation that was written in German and I just copied all the words down. I wouldn't have any really understanding of the scientific explanation. But I could write it all and repeat it. And that what you've got frequently in art projects is a duplicating of the physicalness of it without the conceptual understanding or the conceptual building that you're talking about. Is that correct?
Right. That's exactly, I think, the distinction we're trying to make here, is that these kinds of depictions often don't have underlying them any kind of mechanistic or causal connections between and among the parts that would help someone understand something further about how a system works. That's not to say they're always lacking that, but we just find that is often the case. And so when we put the focus on the creativity behind using art doodads to represent the mitochondria versus the cell wall or whatever, that focus isn't quite the right place for this kind of intellectual furthering that we're hoping to do here.
And another comment I just want to add on to that is that I think for us in particular, it's very important that the models are purposeful, that they're doing work to answer a question or predict something that is not possible. So just using a cell model to just illustrate a cell is okay, but it's not. But really, it's not truly a scientific model unless it's used for predicting the distribution of the cell, components, or how those components work with one another, et cetera, et cetera.
Thank you very much. Now, we had Tina bringing up this aspect of, how do models fit in you know, in terms of the application of them, and then Kathy adding in how are models actually used during inquiry, and Christina, I think you had some things you wanted to talk about with regard to that.
Right. So this is related also to the observations, patterns, models triangle that Cindy was talking about earlier. So where do models fit in terms of predicting and explanations and things like that? And we're going to have some really good examples to show you a bit later. But so it's a little bit complicated, but you can sort of think of a cycle of going basically up and down the application and inquiry processes, and models fit in basically all along the way. That you might start off with an initial question. You'll have an initial, mental model or idea, piece of a model in your head for how something works, and you want to test it. So you do some inquiry to test it. You look at the patterns in the world, and then you test it against that. You revise it and apply it to an explanation, again, test it again. So it's sort of a cyclical process. Does that make sense?
It does to me. Great. Thank you. Let's see here. I was pulling up another question here from my set. I just covered up my list. Too many open windows. Let's go back to the discussion sheet here. Richard brings up, it seems that teachers and students confuse models with levels of reality. Which one is real? For example, the Bohr model and things like that. Do you want to comment about how that all fits into the discussion of modeling and how students have this aspect of, what's the right answer? Cindy, if you would like to.
So I think this is a great question, and one that we all, I think, struggle with a lot in science classrooms, in that students want to appeal. They've been trained through their schooling to appeal to some sort of outside authority about what is right and wrong. And really in the process of modeling, what we're trying to help them do is develop a set of criteria that the community can use to judge not necessarily the rightness or wrongness of a model, but the fruitfulness of a model. And so if you think about in science, scientists judge these ideas based on how helpful they are in furthering their investigations and sense-making of the world. And so there's no way for us to know, or for anybody to come in and say that is the correct model. But what we can say is it's the most useful model we have at the time for making sense of this phenomenon. And so this gets a little bit sticky as we get into some different levels of science, and that even in the sciences, sometimes there are competing and concurrent models that are different from one another, and scientists will use one in one case and another in a different case, depending on what it is they're trying to do and the kinds of predictions and questions they're working on. And so this notion of reality, I think, is one that we need to think hard about, and how that's presented in classrooms and conflated often in classrooms with teacher authority, that students want to look to the teacher as the authority and the arbiter of right and wrong, and that really in these kind of communities of practice we're trying to develop in science classrooms, we want the community to be the arbiter and the judge of how useful or helpful an idea is in furthering our sense-making aim.
And I'd like to add, in the community, we have particular bets, or we have particular values that the science community shares about what some of those agreements are. So, for example, we want to make sure that the model is consistent with the evidence, the best evidence that we have for what's going on. And we also want to make sure that the model is able to explain something about the phenomena. That's sort of what the most useful model is that Cindy was talking about. And several other things, like we want it to be generalizable, et cetera, et cetera. So there's definitely criteria that are useful for that.
Great. Why don't we go on and have you show us some of the examples. Well, actually, first we're going to take a quick poll here. Bryn, if you want to get the poll up, we'll pull this up together.
Thanks, Ted. And everyone, your poll buttons are now active, so I'll pass it over to Cindy to introduce how she'd like people to respond.
Sorry, I need to turn on my talk button. What we're trying to think about now is really thinking, pushing forward in our talk here to some examples where we will exemplify a sequence, and we want to hear from teachers here about how and when they address models in their sequence. And so these choices are just, is it sort of something that comes at the end to review? Is it something that's woven throughout? Or is it not so much used as a review tool, but used as an assessment tool? So those are sort of the choices.
It looks like we've got responses from most everybody, Cindy, so I'll go ahead and lock those and publish them to the whiteboard so you can take a look.
Oh, okay, and so what we see here is exactly what we're hoping to emphasize in our next little bit here, which is that it's really the one way to think about modeling in the classroom is to really infuse it and use it as the unifying thread that adds coherence to the sequence of instruction. And so we'll talk a bit more about that. And I think that the example, or the poll option A, is often what we see in many classrooms. It's sort of to say these ideas are presented, and then we show students some sort of representation, almost as a memory tool rather than as a reasoning tool. And so that's the kind of distinction we want to make here. So what we've done is we've thought about the work that we have done in classrooms, developing curriculum, and the curriculum that teachers with whom we work, the curricula that they have developed, and we've kind of come up with an idealized sequence. And we put this word idealized at the beginning because we want to emphasize that it's not certainly the only way through the path that you might take when you're engaging in modeling in the classroom, but rather it's a way of just kind of doing this check about how we're moving from one kind of segment to a modeling process to another. So the first part of the sequence is to think about the central question or phenomena that's driving the unit, because something Christina said earlier that I want to reemphasize is the notion that we're developing these models for a purpose, and that purpose, it's very deliberate, and that is set up by how we begin the unit and what it is we're focused on in the world. We get some ideas out on the table about what our initial models are, and then we spend a lot of time in these kinds of classrooms investigating and gathering more empirical information that can feed into our model, revise it, alter it, elaborate it. And that while we're doing that, we also need to be attending to some theoretical ideas. And those theoretical ideas may be introduced by the teacher to help students further their thinking. It's not to say that we think students are going to reinvent every big idea in science, rather that they need to be engaged with critically examining those ideas, how they are derived, and pay attention to the evidence from the natural world, and how we can couple a number of ideas and think about the relationships between them that help us explain some phenomenon. Then as we move through this process, students often have slightly different, sometimes radically different ideas, and that part of the process, the cultural practice in the classroom that we're trying to get to is an idea about evaluating ideas, coming up with a consensus that is going to be the model that the class moves forward with, and then using that consensus model and applying it to either the original phenomenon, a tweak of the original phenomenon, or maybe perhaps a new phenomenon. So we're going to go through a couple of examples of these kinds of sequences. Christina's going to talk about a 5th grade unit on evaporation and condensation, and then I'll come back and talk about a high school genetics curriculum.
Okay, so I just want to emphasize also that we're practicing what we're preaching. we only have the opportunity today to really talk about 2 of these units in depth, but there are many other options at the elementary and middle school level. I've worked with electricity and light and ecosystems to develop this kind of sequence around students modeling. In this example, we also chose to pick one physical science and one life science topic to illustrate today, so I'll be doing the physical science topic. And the modeling around that students are engaged in is around diagrammatic models, but as I said before, students can use graphs and data and representations to do data modeling that can help them represent their ideas about patterns and change as well. So anyway, this unit is about a 2-month or 8-week unit. This is one of my 5th grade teacher collaborators, and this is an example of a diagrammatic model from one of the students in the unit. And so let me just tell you that this unit follows the sequence that Cindy was talking about with a central question and all the rest of the steps, and I'll just go through each one of those and show you what that actually looks like. So the central question at the beginning of the unit is really a phenomena that kids can't answer but just with their prior knowledge. So for example, in this situation, the anchoring phenomenon central question is, would you drink the liquid in a bottle cap from a solar still? So a solar still, I don't know if some of you know what it is, but it's a device that is used in many parts of the world to clean dirty water. And so it's a very important piece of equipment, and it uses dirty water at the bottom, evaporates, condenses on some surface, and then gets and then drops into some container or device that you can use then to use for water, for clean water. So, but the students don't know this, and so they have these solar stills around the classroom with lots of dirty water, and they're asked, would you actually drink the liquid in the bottle cap? And they don't know what the answer is, and we don't really want them to be trying out drinking out the liquid in the bottle cap without knowing more about the situation. So that, so then at the next phase, that sort of launches them into this idea of, well, how are we going to figure this out? So then we ask them, well, let's pick this system apart a little bit more, and let's look at one part of the system. Let's look at where this dirty water interacts with the air around it. And let's think about what might be happening. And so we actually pick a simpler question to ask them. What do you think happens when other water might disappear, or other liquids disappear? And so we ask them to draw an initial model of evaporation. And so this is an example of a student drawing their initial model of evaporation over time. And what's typical here is that you'll see some water at the beginning, some arrows with the words often water. Here we've got water vapor evaporating. We've got a heat source because they often think the heat source is absolutely essential, and then water disappearing. And that's fine, but it doesn't really say how this is happening and what's really going on. So in the next phase, we say, well, that's fine, but we don't really know much more about what exactly is going on. So let's do some tests to figure out whether it's disappearing at a particular rate or where it's going and things like that. So at this phase, they do some empirical investigations, and these are rather strategic to address some of the core ideas that they have. So for example, they have a container of hot water and cold water, and they're trying to determine what's going on with the water in those containers. Now we use electronic probes, and those probes are very useful for determining the water vapor levels or the humidity levels in the containers or the hoods around them. And so they very quickly start recording that, in fact, the hot water, the water vapor in the hood is going up. The levels of that are going up. And in fact, the hot water levels are going up faster than the cold water levels, but they're still going up even with the cold water. So we're getting some sort of measures of what's going on in the world around these situations where the liquid is coming in contact with the air. There are other empirical investigations. We use scales that show that over time the containers with the liquid are getting lighter for evaporation. And we also do this, but you don't have to have fancy equipment. You can use, you can look at the water disappearing over time. It just takes a lot longer. And also there There are these strips called cobalt chloride strips that can be used instead of humidity detectors that are not electronic that show the presence of water vapor in the air, and we use those too. Just want to mention that for the second half of the unit, the first half is on evaporation and the second half is on condensation. This is a particularly useful time to have some sort of device to tell you what's going on with the water vapor in the air. Turns out that if you stick a condensing object in a hood and measure the water vapor levels or the humidity levels, they'll actually go down. And that makes sense because it turns out the water vapor in the air is collecting and condensing on the object. And if you use a scale, you can also see that the measures of the scale go up as well. So they conduct these empirical investigations and they revise their models again. What do the things we just found tell us about our models? Well, it turns out that they tell them often that the sun doesn't have to be there, that in fact the water is evaporating, it's just that the rate that it's evaporating is slower or faster, and various other things about how the conditions under which that happens. So they go back and they revise their models and they take out some features that they don't think are important and they focus on others, and they really focus on empirical evidence, which is really key. But they can't figure out from there exactly how and why this is happening. They can only figure out what the conditions are. So at this point, we introduce some scientific ideas to really help them leverage these in their models. And so we use computer simulations from Concord Consortium. We use very simplified ones, and we introduce this idea of bits of matter. So bits of water. It's right at the level when they're starting to think about what's happening to matter and the invisible aspects. Models are just perfect for this. And so finally they start to see that water is made of these smaller and smaller bits, and they're so small that you can't see them, and it turns out they're moving, and in this liquid phase they're moving across one another, and it turns out that if you introduce this idea of the model that when they come in contact with a gaseous surface, they start to spread out into the air, and they're so small that they float and they move around, and in fact so it means they don't disappear. They go from the liquid into the air as they're moving around, and these models really help kids visualize what's going on and give them new ideas for what's going on in a way that they're very excited about. They've never really thought about it this way. They will literally get up out of their seats, jump up and say, "Oh my God, it's bouncing," and things like that. So they get pretty excited. And so then we ask them, we say, well, you've got all these new ideas about how this happens. What do you think is really going on? Let's go back and revise your models again. This diagram on the left is actually a diagram of the evaporation model that a child had before the simulation, and this is a diagram after the simulation. And so you can see before we have arrows because the child knows that somehow the water is going in the air, and it's showing faster and slower rates with a number of arrows. But here we're seeing that they're adding particles. They realize that the particles of water in the liquid are now actually going into the air in particular ways. And they have rates for various, whether it's cold or hot. So the students evaluate and revise their models. There's a point at which in the curriculum they go to each other in class and they evaluate one another's models as peer groups, and they share and compare and contrast. And there are particular norms that need to be set up for that. And then at the very end of the unit, towards the end, they have what's called a consensus model. And on the left is a consensus model a small group did of evaporation, and on the right is a whole group consensus model around condensation, because the second half of the unit's on condensation. So I'll tell you more about these consensus models in a minute. But they have to decide what the best, most important, and useful parts of their models are to represent so that they can use this. And in the end, they use their consensus model to explain and apply other phenomena. So they go back and try and use that model of evaporation and condensation to explain what's going on in the solar still. So this is a diagram of a child that was trying to explain what happened in the pre-test. They didn't really know very much. And this is what's going on in the post-test when they're applying their models of evaporation and condensation. You can see now that they have ideas of particles in the air evaporating and particular processes over time that happens, that it's condensing on the plastic, it's sliding down, and then an explanation derived from that the dirt can't evaporate, so the water in the catch pan is clean. So that is the sequence overall. It may be similar or different from the ones that you use in your curriculum. Overall, you'll find that on average this covers less content per se if you only think of it if you think about it in terms of topic. However, there are lots of things in the unit that are addressed. So it's asking students to make sense of empirical data in very rich ways. It's not just one experiment to illustrate, but multiple experiments to test various components of the models and theories. And we're asking them to embody their ideas in these models, to peer revise and evaluate, and to have whole class conversations about what the consensus is and how that should be applied. So I just want to briefly show you how this happens in actual talk in the classroom. This is my colleague, Mrs. M. In her 5th grade classroom. She often has students work in peer groups to construct and evaluate their models. So here, this is halfway through. The sequence is about class 11 out of 22. This small group of students is constructing their model of evaporation. And she says to them at the very beginning, we're going to take the best of the models, we're going to mix them up and put them together. So this group, made of Melanie, Andrew, and several others, says, okay, we're going to have color, right? So they're attending to this issue. I saw several of you talking about this idea of sort of visual appeal. That never goes away, but they do tend to think about it in other ways as the class goes on. They're trying to negotiate what they should model. They're going to be thinking about different temperatures. So they're really trying to think about the empirical conditions that they thought about and talked about earlier. Yes, hot and cold. We should put the humidity to show that hot water is more humid, to show that hot water evaporates fast and stuff. I have an idea we could do humidity but still do slower and faster. So they have a slight disagreement about how they're supposed to capture that, which they resolve. But all right, Zeta, you do the honors of water vapor. They also know that they're supposed to talk about or embody this in water vapor. They don't really justify their ideas very much at this point, but they do have some sense for what should be included and why. And this is that consensus model. They decide to have a hotter liquid that's evaporating over time before, during, after, a colder liquid that's evaporating. They decide they're going to have arrows to show the process. They have particles that are showing up in greater volume afterwards, and they have humidity levels over time too that are showing how they're increasing. And so they've negotiated that that's a good place to hold some of their ideas about how this evaporation happens. But they go on in the unit and they evaluate that as a class. Here's that model being evaluated, and the student says, I like how they showed the percentage of humidity. So they talk about that, and the teacher, Mrs. M, emphasizes this, and she relates it back to their investigation. She says that directly comes from the humidity detector investigations, and she talks about how that's evidence. So they start really thinking about evidence as a criteria for evaluating their models. And when they get to their consensus model of condensation towards the end of the unit, they talk about how they want to incorporate things around mechanism. We want to draw water vapor. And Hyun says, but why? And Melanie says, we need water vapor. Andrew reiterates, we need water vapor. And Melanie says, okay, but we need to draw a lot of water vapor inside the container at first and in the air, and then over time there's less and less. And at the end there should be barely any water vapor. And they have basically an idea about how they could show this. Andrew introduces that over time they found in their investigations that it turns out the water that condensed eventually starts to evaporate again, and he wants to show that, which they end up doing. This is not a very clear representation of that. It wasn't very dark, but that's exactly what they end up doing, is they show the evidence in their models over time in this condensing situation. So that's their consensus model. My other colleague, Mr. H, does this as a whole class, and this is an example of a very brief part of his conversation he has with this class about constructing a consensus model of condensation. And he asks the class, well, what do we need to have in this? We have water molecules in the air, it's in a room, it's sitting on the counter. Ethan. So they have this very interesting conversation. Ethan says, we should have water in the bottle. And Mr. H says, what's the point of this? Do we have to have water in the bottle to make condensation happen? What does it matter? He's really trying to point out this question, that Ethan might have this conception that there needs to be a liquid in the bottle for the object to condense. He asked the class, does it matter? Students are divided to say yes or no. He takes a poll, raise your hands if it doesn't matter. He realizes the majority say it doesn't matter, so he's going to leave the container empty for now, and says to them they can decide if they want to put something in on their own. But then he says, think about the criteria we just came up with. If you want condensation to happen, what needs to be there? Melanie says, it sounds like the bottle itself is cold. It doesn't matter if there's water in the bottle or not. And Mr. H reminds them, where is the condensation coming from? And the students say, it's coming from the air. We figured that out. It's coming from the air. Does it matter what's inside the bottle? No. On the basis of what? What do we need to base this on what? And the students say evidence. On evidence. What did we see in our investigations? And Anderson reminds them, we saw in our investigations that the condensation came from the outside after it's already evaporated, because they had done some experiments with a mirror in the refrigerator, and the mirror didn't have liquid in it, and it's still condensed on that. So that's an example of a whole class conversation engaging in this consensus model construction. In the end, what did students learn? Students learned about evaporation and condensation. It's an incredibly complicated topic, believe it or not. That significantly increased. They learned how to explain their ideas. They realized there's an audience other than the teacher to which they must pay attention. They realized that models need to be generalized to answer other questions, that the real world needs to be consistent with their model. They're paying attention to evidence. And that they need to explain how and why things happen. So they're really getting at mechanism. Those are critical things about science that we want them to be understanding. But they're still learning things. There's still a lot of social norms. This was at the beginning of the year. They need to figure out how to negotiate differences with one another. That's a very difficult thing. They're not used to doing that. They don't know how to do that very well. They need practice. And there's other aspects about details about evaporation, condensation, the particle nature of matter they're still working on. Some of them are still confused about exactly what parts of the liquid water end up in the air. Is that the same or different than the other air particles? And we don't get a chance to clarify all those things, though it turns out that comes in the next year when they're really talking about the particle nature of matter and looking at the periodic table on these things. And finally, they're trying to work on how these ideas apply to other situations. The world is very complicated, whether this applies to nail polish drying or hair drying or paint drying or other kinds of sweat drying. What evaporates, what doesn't? Those are all things the students need to think about and work through. One other thing I wanted to mention is that this really embodies the idea of a model-based modeling in a unit, because students are beginning with a driving question. They're following this initial model that embodies their ideas about what's happening, and they're revising that against empirical evidence and their theories. They're revising that and talking about it as a community with criteria like evidence and mechanism, and they're applying that to answer the questions both posed at the beginning and other questions about the world. All right, so that was a lot of information. I'm happy to take questions at this point to help clarify any of this.
Great, Cindy. We'll start here with one that I just had in front of me. At what point does the teacher correct student misconceptions? The consensus building is great for student-to-student discourse, but it needs to be carefully moderated, is the assumption. You want to provide some insight into that?
So I think Cindy and I both have some good answers for this, so I'll start and then she can continue. Definitely, things come up all along the way, and as a teacher, you have to be fairly strategic about how to do this, obviously. On the one hand, if you correct them at every single moment, they're not going to, along the way, even at the beginning, they're not going to have sort of any incentive because their curiosity is going to be gone. They think you're the holder of the ideas. There's nothing else for them to know about. So you have to sort of carefully guide along the way and sort of help them understand and think about the experiences that they're having in the world. The whole reason why these ideas are useful and accurate is because they're consistent with the empirical evidence and the other ideas that we know. So keep helping them come back to those things later in the unit. What is it that we found out about? Just like Mr. H said, what did we figure out about in our investigations? Did we have liquid in all the containers that condensed? What was it about those situations that made those objects condense? So he did that, but you can also strategically help students question one another. So Mrs. M strategically does that by asking students to compare and contrast small group consensus models. So she'll put them up on the overhead, and she'll ask one another, do you have any questions about this? I noticed that this one, what do you notice? I noticed that this one has a lot more arrows coming out of this model of evaporation, and this one doesn't. Do you think that matters? What is, things like that. So I would say definitely be strategic. Try and pick up as much at the end as possible and reiterate the criteria that we're working with. Cindy, do you have any more to add?
Not much. I think that's a great answer. And I just think that the key is often not just not telling students that they're quote unquote wrong, but helping them come to see it themselves. And that's a huge difference if you want to create a classroom environment where the students are feeling safe to voice their ideas and play around with them and toy with them and struggle with them. That's the kind of thing. And so often it's the question you ask back rather than the telling that you do. So for example, I was working with some Earth, Moon, Sun astronomy students working on that, and they came up with an idea about the moon that had it kind of hovering over a particular part of the Earth all the time. And so rather than saying, coming up to them and going, well, that's obviously wrong, I said, well, let's think about, okay, so that may explain the phenomenon that you're talking about for the perspective of where they were hovering it over, which happened to be Hawaii. But what about the folks in Europe? What are they seeing at this point? And just asking that question and walking away allowed them to come to see that what they were doing couldn't explain the phenomenon that we were trying to account for. So that's that kind of thing that you can do and encourage and show students how to do that for one another. That really can help us move forward.
Great. I mean, I think we've got some other things we could follow up on that piece, but I think it might just make as much sense for Cindy to show her example, because I think they're general points here. So why don't we go on to our next area?
Okay. So I'm going to be talking about a high school biology vignette. I'm going to do this in a little bit less detail than Christina did, mostly because our time is limited today. And so just to give you a little framing, I'm going to be talking about this high school biology example of classical genetics. And I do want to acknowledge Sue Johnson as kind of the innovator around this particular sequence, which is the first place I was introduced to modeling in the science classroom 15 years ago, and it remains one of the most compelling examples that I know of, and I've used it in many, many classrooms since then. And so I'll be talking through this example that begins, again, follows fairly closely the sequence we talked about before. It begins with a driving phenomenon where students look at some family history data, and I'll talk about that in a moment. They construct an initial model, heavily guided by the teacher, and then engage in empirical investigations. They evaluate their models, come to some consensus, summarize them, and return to the family histories, and finally they apply their models to some novel pedigrees and genetic data. So I'll go through each of these in turn. So they begin in this case, in this classroom, and again, this is high school, 9th or 10th grade biology, where students are given some information that's in the form of a family history kind of data sheet that a family would fill out if they went to a genetics counseling clinic. And their task is to take these forms that this fictitious family filled out about their family history and transfer that information into the form of a pedigree. So what they're trying to do, each family history is focused on a particular genetic condition. Those conditions are things like PKU, brittle bone disease, which is called osteogenesis imperfecta. There's one on blood types. So things like that, where the sort of puzzling issue is the family has a child and they're trying to figure out if this child may or may not have the condition. And they're doing that by looking at the rest of the family. This is assuming we can't just genotype them for it, which we could these days probably. But so they find across the pedigrees they make, so each group gets a different family, and so a different pedigree emerges from the group. And once they get their pedigrees on the wall, they notice some patterns in these pedigrees. So a range of ways in which things seem to get passed down from one generation to the next. And those patterns are things like sometimes both parents are affected and the child is, sometimes only one parent is affected and the child is, and sometimes neither parent is affected and the child is. And so trying to understand what some of those patterns really look like. And so eventually we get to a driving question of why do different conditions seem to get passed down in different ways. And this is going to guide our investigations as we go forward. They construct an initial model using actually Mendel's original data coming from his manuscript. And they take a look at those data, and this process is quite heavily guided by the teacher, where the teacher is helping them see and squaring up what Mendel found with what we know about meiosis. And so the students have already have a very robust conceptual model of meiosis that basically states that each individual has some information from mom and some information from dad for each trait, and that which piece they get from mom or dad is random. And they have that already, and they're squaring that up with some ideas that Mendel had about what he called factors. And you can see down here under this thing called the Pocket Mendel, where they are using their ideas to map genotypes to phenotypes. So if there's an allele combination, you could have two different allele combinations that map onto variation A and one allele combination that maps onto variation B. And this is basically where they get with their model after some guidance with the teacher. That's their initial model. And then their job is to take that model and apply it to data that's generated from a fruit fly simulation. So they cross fruit flies and they see, first they're using Mendel's model. Can they determine what's recessive and dominant based on the data alone, no information about the genotypes? They have to derive that information and figure out what the genotypes are of the individuals. And eventually they get in the simulation to a place where they can't use Mendel's model, because Mendel's model is designed to account for phenomena in which there are two variations for the trait, dominant and recessive in our lingo, genetics lingo. But they come across in these simulations cases where there are 3 or 4 variations for the trait, or cases where males seem to be affected differentially from females. And so now they have some anomalous data to explain. And what they are asked to do then is to think about their model that they have already and what can they change about that model. And they eventually do that by revising their models, mostly the allele combinations. And so they're constrained, again, by a model of meiosis they have that helps them think about the fact that they're only going to have 2 alleles per individual, but that those alleles can interact in a number of different ways. And if you have more than 2 alleles in the population, then you start to get a number of different outcomes. And so they make these model revisions within their groups, working on particular phenomena, fruit fly crosses, and then they share those and come to some consensus. And eventually the class comes to a set of models that can help them account for a number of genetic patterns in families of simple dominance, codominance, multiple alleles, and sex linkage. And they come then to a point where they can apply this set of models to the initial family histories and come to the realization of which of the conditions they looked at might be governed by simple dominance, multiple alleles, codominance, etc. And they can engage in argumentation about which model should be applied to which family, and it's a really robust conversation in the classroom. And then at the very end, they take those models and they are presented with brand new family histories and pedigree data to explain. And so here's an example of a student looking at an albinism family history presented as a pedigree, and they're looking at this cross between K and L, and they say, I see that that it must be recessive, that being albino is recessive. And the instructor says, well, how do you know that? And Paul says, well, it's the only way, because these 2 are unaffected, K and L, and they have an affected child. And the only way that could happen is if they were, in our lingo in that classroom, he says 1-2s, but what that means is heterozygotes. And so he's reasoning about where the alleles came from that made Q affected, and reasoning that K and L must have had those alleles. And so this is the kind of process we go through where the students come through a series of model revisions and elaborations that allow them to explain a wide range of phenomena based on the initial question they had of the range of ways that things seem to be passed down in families. And so they come to see that it's not random. It's not totally random. In other words, any given disorder is going to follow a particular model, but it's not. But there are a number of models at play in genetics at any given time. And then they further in this course they go on to talk about the molecular level and come back to how the molecular level relates to the allele level. And so what they've done in this course, in this unit, is thought about the details of these 4 different classical genetics models, and they've learned them in a quite powerful way. They've reinforced understanding of meiosis. They've coordinated a lot of simulation data and evidence and had those feed into their model revisions, and they've engaged in that argumentation and communication process as they go. And so this is another example of taking students through this process where the key intellectual activity in the classroom is the development and use of models. That's what they're doing, and if you were to tap a student on the shoulder and ask them what they were doing, they would say, we're developing models to figure out how things are passed down. And we're applying those models to different organisms and traits in the natural world. So again, we can stop here and pause for questions.
Great. If people want to throw some questions into the chat, it'd be great. I'm going to start with one that's fairly large and maybe simple. What's the relationship between models and theories in terms of all of this? Theory is another term we hear a lot in science education and used in science as well. And Christina, would you like to take a shot at that?
Sure. I was hoping Cindy would jump in, but no, this is fine. I'm not a historian of science, so you probably shouldn't quote me, but the way that I think about this is that models are parts of theory. So they tend to be, they're theory-like in the sense that they address parts of theories. But so for example, let's pick the Bohr model of the atom. It doesn't embody all of the theory, particle nature of, the theory of how particles interact and what the atomic nature is, but it embodies some critical aspect of it. So that's how I think about it. Cindy, do you have a better definition?
No, I think that's good. And I think the way a lot of times we think about it is that models are sort of instantiations or realizations of theoretical ideas. And in that sense, they are one way that some historians think about it, or philosophers think about it, is that theories are sort of made up of families of models. And that the way in which you instantiate particular theoretical ideas, you may have a number of different ways of doing that around a large theoretical idea.
Great. Excuse me. Another question here to sort of build on the conversation we were having last time. Maybe I'll get Cindy to try this one first. Is what are the skill sets that a teacher needs to be putting in place and having in place from the teachers who are successful in engaging in this approach to the teachers who may, at least at first, struggle? What is it that those struggling teachers need to develop in their repertoire to engage in this sort of process?
Well, it's a question I've been trying to answer for the last 6 years, and it's not a simple one. But the key, I think, is there are a couple things. One is that they are creating a classroom in which the intellectual activity is centered on sense-making, and collective sense-making, in fact, where the students see their job as figuring out how something works, and that their job is to do that with all of their minds and in the best way they can, and that it's not a competition, but rather that they all get further if they take bits and pieces of different people's ideas and put them together and evaluate those thoughts against what they already know and the evidence they're gathering, and just continue to chip away at the problem. And it's really in classrooms that see their job as that rather than as quote-unquote learning something so that they can put it on a test, or as as being about almost a competitive environment where they're trying to get the answer before someone else. Those are the kinds of things that detract from what we're up to here. And when teachers can effectively get their students all on the same team in terms of pondering and answering, coming to some ideas about why something happens in the natural world, that intellectual curiosity that is sparked during that process gets you a long way toward getting kids to do the kind of reasoning you're asking them to do. And so it's really about developing that classroom culture that's about figuring out, using our best ideas, all of our best ideas, how something works.
Great. So at that point, let's move on to our last example here in piece, and then we'll have a few more questions at the very end.
Okay, so one of the things we wanted to kind of come back to is this notion of sense making that I was just talking about. And that if we really want our students to be making this kind of progress in their science classrooms, that they need to see the scientific enterprise as being about sense making, and that students need to be engaged in that process themselves, not hearing about how others have done it in the past. And so what are some strategies we can use in our classroom to help us to cultivate and develop that kind of environment? One is that we have a driving question, that posted up in the room, made prominent and made sense of at the beginning is what it is we're trying to figure out. That there's some big important idea that provides that thread and coherence to the unit. And that we can develop models that can help us address how they work and why they work the way they do, the phenomena that we're asking questions about. And so therefore that sort of begs the question that, or begs the point that we want phenomena to be present and be the focus in the classroom, so that there is something intriguing that the students are working toward explaining. They're trying to relate what their developing theoretical ideas are to something in the world that makes, and it's that sense-making process between the two that helps. That our first idea is probably never the only or the best way to think about something. And so that this notion that we engage in evaluating our ideas and pushing them and revising them as we go is an important aspect of modeling. And then, again, this notion of explanation as being the thing we're really driving toward, and that we can do that best when we put all of our minds together. And that so we need to be talking to one another and creating a safe environment where students can argue about their ideas and the connections they see between the evidence they're collecting in the classroom and their emerging ideas safely and productively in the classroom. And so those are some thoughts about some strategies we might employ. I'm feeling like we might not have time for this poll. Should we just keep going, or?
Sure, Cindy, let's go ahead and move on to the next slide.
Okay, but just to say a little bit about this poll is to say that I think that one of the things that we have seen in our work with teachers is that one of the things that it's really all of these things that they struggle with. But one of them, this A issue, is that many teachers haven't experienced this kind of pedagogical environment themselves, and so they're not really sure they understand what modeling is in practice, in scientific practice, and therefore they're not quite sure how to help students do that. And so the more examples we can start getting out there and sharing among each other, among the science teaching community, the better, I think. Okay, Christina.
All right, so we have some ideas about how we can help one another engage in modeling practices in the classroom. And one is this sort of driving question and the focus on powerful science ideas. We really think that's the key thing. One of the key things is rather than covering a whole lot of more minor issues, is to try and find coherence with a really big idea, something that students need to know rather than it's nice to know. And use models as a way to follow up and help students revise their ideas and maintain conceptual coherence throughout the unit. So for example, I'm working on helping revise a third grade FOSS unit that covers just a ton of different topics. about water. It's got a theme of water. Some of you might be familiar with that. Well, we're rethinking the unit to focus on a model of a system of how water interacts with particular features in that system. How does water interact with the gas in the air around it? How does water interact with Earth systems in particular ways, and how does it interact with heat, and how might those things cycle and affect one another? So that sort of brings coherence to that unit, and that might be an effective way for some of you to think about it too. Students in general tend to think better, and there's some evidence that they can learn more deeply. So even if those bits and pieces of information may not be included or not included as well, they might know the other stuff better, and they might do better. And more importantly, they're likely to learn these 21st century skills involved in the practice that we think are really important for lifelong productivity and engagement. So working and negotiating with others and adhering to a set of explicit norms. All very important things. One thing I just wanted to share briefly with you is that my colleagues and I have done some work on evaluating students' modeling practices, and we've developed a learning progression. It's fairly it's somewhat in the early stages, but I just wanted to give you a sense for where kids might be at various levels in their modeling practice. So at the very early elementary level, students refer to models in terms of right and wrong and replicating the phenomena. Over to level 4, which is an extremely advanced practice that you might not see until perhaps college or graduate school, hopefully high school, but you never know, where students are evaluating competing models, attending to counter evidence, and considering changes to models to develop questions that can be tested against phenomena. We're seeing kids primarily at levels 2 and 3 at the upper elementary and middle school level, where they're learning how to fit their models against evidence completely and provide mechanistic explanations, and as Cindy said, sort of using their models to make arguments in making sense of the world. And so that's something to think about as you're engaging your own students with modeling practices. So in the end, summary of main points. Modeling involves testing and revising models to make sense of the world. It works with the other practices by establishing ideas about how and why the world works that can be tested and revised. So in that sense, it forms the cornerstone of all the practices. That testing process involves social aspects of working with others to evaluate and persuade one another of the best ideas and evidence. And in engineering, models are extremely important for solving problems in that sense. And we encourage people to focus on modeling by choosing the most important science ideas and developing a model-centered instructional sequence, and then continue to monitor and respond to students' ideas and practices throughout. And we are pretty confident that learners will develop skills and knowledge focused on how and why phenomena occur and the importance of evidence, and thinking about how models can be applied in consensus and persuasion skills. We want to close with some resources that might be useful for you. We have a couple of papers and chapters that might help in thinking some more about this practice. There's a book. We also have a couple other things. Our colleague Mark Winchittle has this wonderful website that has tools online, videos, and tools for middle and secondary teachers to help them engage in these very rich practices. We also know there are some curriculum materials that might be useful, NSF-sponsored ones like iQuest at middle school, engage students in particular practices, and some of the ones that Cindy has worked with are also interesting and can be very useful for that as well. And also, I just want to make a shout out for our colleagues Leona Chavo and Rich Lair, who have done some elegant and very fabulous work at the elementary level around data modeling as well. So those are some other resources. And finally, we want to provide our contact information in case you ever want to get a hold of us for any further questions. And that's it.
Great, thank you very much. I think this has been a very useful piece here. Let's get a chance for any last-minute questions people have to put up there. I'll start with one here, which is to what extent is mastery of the content a really important piece for teachers in engaging in this sort of work?
I can answer that, and I think Cindy might want to pass at this also. They're not separable, right? I mean, content and practice they go together, and they only make sense when they're together. So I would say that the content itself, the knowledge, for example, in the evaporation condensation unit, about how particles exist and how they interact and spread out and move, is really critical to understanding and figuring out the question of how these phenomena are occurring, and that process of how the class figures it out is part of the way that they determine that. And so those things are intricately linked. Cindy, do you want to add?
Just to agree and to say, and I'm noticing a question about time coming up, and of course that comes up in our work as well with pretty much every teacher I've ever talked to says, well, obviously a modeling unit takes more time. And I guess my response to that is really related to this notion of mastery of content, and that is if you take a bit more time but the students emerge with a deep understanding of the relationship between the theoretical ideas that we have about the world and the empirical evidence that we've gathered about the world, and how those things come together to explain a question or a phenomenon that we're focused on, that it's worth the time. And it's well worth the time. It's a much better use of our time to get to that kind of mastery. And if we could imagine a K-12 environment in which that was really where we got with students, we could still get to all the content we care about over the 12 years. Rather than, we were just talking with some teachers yesterday about this sort of seeing a density activity in a 5th grade and a 7th grade teacher saying, I do that exact same thing in my class, and it's sort of like, well, why are we doing the exact same thing over and over again? It doesn't appear to be working. And so I think this notion of mastery is really an important piece of what we can achieve through a modeling environment, and a whole bunch of other things about intellectual curiosity and about how the scientific enterprise works also come along for the ride.
So the two things I'm hearing from you there are, one is that the learning that goes on through this process is something that stays with students, and so that, it's not like a few days after the test that kids no longer remember it, let alone the next semester. So I'd like to comment about that. And then I'm also curious about when you look at that progression, you've talked about different places of that progression. I know, Cindy, you're in California, Christina, you're in Michigan, so you're both, in some cases, even at the higher grades, working with students who haven't had this type of instruction earlier in their career. And so we think there's got to be some sort of load to just getting students engaged into this sort of mechanism. And if that started at the earliest grades, there would be a lot of potential there. So maybe Cindy starts commenting on that piece, and then Christina fill in.
Yeah, I agree, and I'm sure I'm preaching to the choir here, that our schools have cultivated an environment of passivity and a notion that knowledge just comes from the teacher to the students. And that's, of course, not at all what we know about how learning actually occurs. And so a classroom like this is really taking advantage of the best ideas we have about learning and about how one actually learns meaningfully. And so a classroom that is reoriented around sort of this collective sense-making is quite powerful, is a powerful learning environment. But it does go counter to what many, many students are experiencing in school these days. And so we have to think hard about how we situate the class and help the students do that switching. And we know they can. We know that they can come from a super passive class and jump into a class that requires them to be active learners, and they'll do that if they understand what the expectations are in different classrooms and with different teachers. So it's not like just because they haven't had a lot of it, the deal's done. We can disrupt that, and we have to.
So I also just want to share some really exciting work that I'm doing. We're following up the students that were in the 5th grade classes with Mrs. Mrs. M and Mr. H into their 6th grade classes this year. And in this class that we just were in the other day, the half of the students that had participated in modeling before were amazing at I mean, they all jumped in to ask questions, and they wanted to test things, and they were willing to share their ideas. And they were all over, I mean, it wasn't just that they were especially high achieving students. These were a variety of students with a whole lot of different backgrounds and lots of different comfort levels with sharing their ideas, and it was just amazing to see how used to the environment they got with being able to share and negotiate ideas and test and question and use resources for that. So I'm hoping that I'll be able to follow up on that and get some more of that data out there so people can be convinced that this can really work well.
So, I mean, this isn't even really the last question. I'm just trying to get a quick follow-up on here. Would you encourage teachers who are engaging this to think about doing this as teams, and you know, if you're in elementary school, getting the 3rd, 4th, and 5th grade teachers together into engaging this sort of process, or in a middle school working across grades, that there's synergies and features that are really useful in all of that?
Absolutely, and we found with the teachers with whom we work that they find that kind of teaming to be incredibly powerful for exactly the same reasons I was talking about in the classroom. It's getting a bunch of brains on the problem, and getting a whole bunch of professionals thinking about what is the best task and how do we sequence and order this, that they get more traction. And then, of course, when you have teams at the same school where the students see similar things occurring from one grade to the next, exactly what Christina said is what we have seen too, is the students develop amazing capacity to do this. And then they begin to expect that from their classes, and that's really powerful.
Great. So what we're going to go through here, I want to really thank Christina and Cindy. Just want to point out some places you can get additional information about the standards and the practices. Obviously, this web seminar will be put up on the NSTA Learning Center. I encourage you to send your colleagues to it. NSTA is really trying to, with NGSS, is to have teachers involved in the process and to be prepared for when these standards are eventually implemented. You can go to nsta.org/NGSS to connect to any and all information we have around the Next Generation Science Standards. We are, as we've talked about, doing a whole series of web seminars on the practices. Here is the list. Our next one will be on October 9th with Rick Duschel, talking about planning and carrying out investigations. And then we'll go from that web seminar on to a whole other series. If you participate in the whole series, either by attending the live presentations or reviewing the archived sessions and completing some reflection questions, you can actually get a graduate credit from Shippensburg State University. More information of that can be found on our website and also on the Shippensburg website. We have set up in our Learning Center a community forum specifically devoted to NGSS, and discussions about these web seminars are encouraged to take place within that, to carry on the conversation from this session. We also will be having sessions about practices and other things in terms of the Next Generation Science Standards at our 3 area conferences, first in Louisville, coming up October 18th through 20th, then in Atlanta, November 1st through 3rd, and in December 6th through 8th in Phoenix. I encourage you to attend those. As I mentioned earlier, you can find the framework itself or a reader's guide prepared by NSTA, and also journal articles that we're doing about the framework and the standards. So with that, I'll turn things over to Bryn and go from there.
Thank you, Ted, and I'd like to thank Christina and Cindy as well for the fantastic information, and it was really rich and engaging content this time, and I really appreciate your information that you shared with us today. I'd also like to thank everyone else for participating. And to the sponsor of today's web seminar, the Carnegie Corporation of New York, thank you. We'd also like to thank the administration of NSTA for their support for web seminars. And I'd like to remind everyone to check out our website to take a look at upcoming programs. You can visit learningcenter.nsta.org/webseminars to register for everything coming up on our calendar. I'd like to invite everyone to join us again for another web seminar, and thank you for your participation.